Energy diagrams. Let's have a look at one. This is a typical energy diagram. We've got carbon monoxide reacting with nitrogen dioxide, transferring in one oxygen atom over so that it ends up being carbon dioxide and nitrogen monoxide. If you plot energy versus reaction progress, and that's what they do for these energy diagrams, you almost always see a activation energy. You're putting some energy in, and then once it gets to a certain point, it starts releasing energy. So as you go up, that's energy that goes in. That means it's endothermic at that point. To this point in time, it's this much endothermic, and that's equal to the activation energy required. So these are your reactants. This is the activation energy required. When you get to this point, you're at the transition state and you're forming an activated complex. This says a lot about the mechanism of the reaction. Look how these have to line up in one big long sequential series of atoms. That makes sense if this oxygen atom is being transferred. So before there was intermolecular force right there, but it's going to become a bond and it's going to break right there. So it gives you a good idea of the mechanism. In fact, that seems reasonable if you're transferring an oxygen atom. However, once you go beyond the activation energy, it starts releasing energy, and it goes beyond the break-even point, and it releases energy overall. Therefore, this is an exothermic reaction. Were it to have a curve where the final state is higher than the initial state, that would be overall an endothermic reaction, one that you have to supply heat to, for example, baking a cake. And you'll see both types. So this is a typical look at a energy diagram. And how exothermic is it? Well, you put some in, but you got it back. And so the difference between this line and this line gives you a measure of how endothermic the reaction is.